Welcome everyone. This is the lecture about introduction to nanotechnology, specifically about nanoscale properties. We all know that there is a huge effect on the properties of materials when we make them too small. And those size effects are, they come out in many different ways. So we'll touch upon some of the parts of learning outcomes of this lecture. Essentially, we look at material properties because material properties like melting point, fluorescence, electrical conductivity, chemical reactivity, they all would change when we look at nanoscale uh, size of any material, whether that's a metal, whether that's maybe clay, many chemicals, many things. When we have them ground to small pieces, their properties change. One important aspect that goes with that is that the surface to volume ratio becomes huge. When we say, as it says, surface size is large. What that results into is that a whole lot of that material comes into contact with the surrounding environment. That surrounding environment may be solution, maybe water, maybe a chemical, maybe acid, maybe just a solution where it's supposed to be dissolved. Now, when you can have different properties in nanoscale, we can easily tune those properties also by changing the size. So the adjustment of the size can result into changing or tuning the properties of various properties of those things as well. Now, when you have so much control on all these properties, we can have very complicated ways of doing things. So let me just give you a big example that how nano scale world affects us. We have seen all these things in different contexts. We have seen mosquitoes that would ride on water, that would walk on water. Their feet don't get wet. We have seen spiders that climb the wall. And if you remember this scene from movie Spider-Man, where the hero, the Spider-Man, gets this nanoscale hair coming out of his finger, which they say, okay, that helps him what you call stick to the walls or to the vertical surfaces. So it's not too far from the reality because all of these legs of or the feet of these things that stride on water, walk on water, or water strider, they have hair on their legs, hair on their uh, those body parts. Not just hair, they have grooves on there as well, which possibly give them hydrophobic properties. So these are real scanning electron microscope images which show this micro hair on the surface of uh, those legs. And when you go close to those micro hair, you see nano grooves over there. So this is something which gives us that, oh, maybe there is something going on more than just uh, their weight of these things or just the presence of hair, but there's nanoscale properties which are giving them those uh, what you call gravity defying properties or qualities. So when you speak about those nano properties, let's take a look at some of those. This list is not exhaustive list. There are many more things that are important or that are especially more evident at nanoscale. But let's just take a look at few of those. So number one is self-assembly. Self-assembly is the concept that in nature things would assemble together to minimize overall free energy. Here are a couple of examples given. One is showing that if you have a very narrow tip and if you have some chemical molecules riding on it, and if you write a line, those chemicals molecules would line up together. And especially this would be more true if that chemical has two different kind of end groups. So like in this case, it's showing there's this pinkish type of molecule or an atom maybe on one side, and then there's green chain. So maybe it is a molecule which has one end like this pink end which doesn't like water, what you call as hydrophobic, and green thing is maybe that likes water. So if you'll put it into a solution of water, you'll see that the those molecules will line up in a way that they would want to keep the water away from those pink hydrophobic portions. That's we'll talk more in some other lecture. There is another example shown here where if you throw a bunch of molecules in water, like the one on left hand side shows all green parts in it. The right one shows green, red, and green parts in it. So again, these are one molecule which has some different portions, some different functional groups in it. So they show that they would aggregate and come together. On the left-hand side, we see they just come together like without any specific order. But the right-hand side shows that they would create a nanostructured, well-ordered shape like a triangle, which will hold some of those water molecules inside that triangle. So which means that is now a 3D kind of a structure which holds the water inside, right? So the water molecules is being held inside. So that's one property that at atomic scale we can design our molecules to show what we call as self-assembly. The nanoscale entities, we know this about graphene or carbon nanotubes, they can show superconductive behavior. Superconductive behavior is if we have superconductive material, we would have no losses in getting the power transferred from wherever we generate power and wherever we use power. So there's lots of power that gets wasted in that. If we have superconductors, our laptops would not get heated because they will not be losing any power because of resistance of those devices. Superconductor mean no resistance at all. The current can flow smoothly without getting lost in terms of heat or in terms of vibration and other ways however we lose energy. So superconductors have nano features. One of the feature of nanoscale materials is we can get superconductors out of them. There's another very interesting aspect which is what we call as nanoparticles. Optical properties. Nanoparticles, very small particles, nanoscale, they, if we reach their size of their band gap, which is a concept about solid state devices, we can start getting different kind of lights out of them. Same material, but different colors of light. For example, this example shows that cadmium selenide and zinc sulfide quantum dots. Yeah, by the way, those nanoparticles where we can play with their optical properties or we can play with the wavelength that comes out of them, we call them quantum dots. Just by changing the size of the same material, changing the size of their nanoparticles of the same material, we can change the light that comes out of them, which is an amazing property. We don't see materials giving different wavelengths unless we change their uh, band gap. And changing the band gap requires we have to mix different alloys. We make different alloys. But this is the fantastic property of nanoscale material that you don't have to add any new material, but just by changing the size of the particle, we can create different wavelengths that come out of that. And that has given us many, many fantastic applications. For example, this is an example of nanoparticles which don't settle down. But that's quantum dots, which would give different wavelengths. Now their size means there is no effect of gravity on them, which means these particles will always be suspended inside the solution. The, and we don't know anything. If you leave something, some particles suspended in a solution, you leave that bottle vial for some time, those particles will settle down ultimately. Even blood settles down if we have a blood in a vial. Think about it, but if you make them too small, the gravity doesn't have any effect. So only surface forces are there which are more uh, evident or they're more overwhelming unless they don't make them agglomerate together, because if they agglomerate together, then that means that the particle will become a larger in size and hence the gravity will start acting. Gravity will kick in. Gravity is there, but if they're too small, gravity has no effect. So that's another. very interesting property of nanoscale, in addition to what we call the optical or wavelength adjustment, like in the case of quantum dots. Another interesting property is wetting. If we can and add some nanomaterials to, say, uh, clothing, they can become stain resistant. They can become wet resistant, which means you can keep on walking in the rain and your clothes wouldn't get wet because the liquid wouldn't get attached to the clothing, so they would never get wet. So this is an example showing where there is just the same cloth where if you put drop water, it will spread and ultimately get soaked. But if you have those nanomaterials, what they call nano whiskers or these, there are many things that have been tried. They would give this hydrophobic property to your clothing, which means they will not let water stick. The water will just slide off the surface because they can't stick. It can't spread. It can't get soaked. So think about it. Having your socks on for, I don't know, for a month without them ever getting sweaty. Maybe you do get sweaty, but they won't be sucked in by the cloths of the socks, and hence they wouldn't get probably they wouldn't get smelly. Anyway, these are application about wetting. Reactivity. Now that's an interesting concept because that leads into the next one as well. If you have a big block, think about it, if you have a big block of say what you call butter, and you put butter into your pan and you want it to melt, it will take much longer than if you could cut that butter block into smaller blocks, smaller pieces, and then if you throw it, the whole thing, it's the same volume like a big chunk, but now made into smaller one, they will melt much faster. Now, if you think about making those nanoscale small parts of the same big block, think about it, without uh, maybe any delay, they will just melt. So that's the same concept when we react something. So if you uh, bring two chemicals or you put one chemical into other liquid chemical and you want to dissolve, want to react, a big chunk versus smaller chunk would make very big difference in their reactivity. So it's a bit, we'll revisit that how does the change in surface to volume has something to do with that. Now, this is an example, big red block, chopped into two small blocks, then chopped into four smaller blocks, same volume, but now we are chopping into smaller chunks. You can chop it into eight smaller blocks. If you think about it, it's the same volume, just making them small. But now, if you compare the volume versus the surface that's available for to the outside world, there's an enormous difference. And if you do a little bit calculation, you can see that if I take a Rubik cube and I say, okay, we just take the three sides that are visible. There are six sides to it, but let's just stick to three sides, which are to the front. And what is the surface of these three sides? We can easily calculate, right? So 3 squared. And now we have the surface of the whole thing. What is the volume? Volume is one side versus one side times the third side, right? If you make surface to volume ratio, all you get is 2. Now, if you cut it into smaller pieces, and now you take two sides and you find the surface, and for all six parts, and you take the volume, the surface to volume ratio is much higher. And then you take even a smaller piece and you say, okay, that's the side, and if I calculate the surface for six places and volume, you see the surface to volume ratio has gone high. Now, what does that tell us? That tells us that if you have nanoscale material, they would have much higher surface available for the same volume. So if we have, say, 1 pound of a big block and same weight, 1 pound, but now the big block is chopped into very small pieces. There's much more surface area available if it's chopped into very small pieces. More surface area would mean, like we were talking about, reactivity would possibly mean more reaction. because now all those surfaces can react. So this is another interesting property of nanoscale materials. All right, so if you have any questions, send me an email. Take care.